In the previous lecture on beta decay, you have seen a brief introduction regarding this process of beta decay. Now, in today's lecture, we will see the actual process of beta decay. At the same time, we will also calculate the Q value of this process. I have told you in the previous lecture that the stability of a nucleus depends on the ratio n over z, where n represents the number of neutrons and z is the number of protons in a nucleus. And you have seen that if there is an unstable nucleus, then definitely this ratio n over z get altered. Then the nucleus becomes unstable. So the cause of instability is of two types. This may be due to the excess number of neutron. When you say excess number of neutron, it means the number of neutrons present in the unstable nucleus is greater than the number of neutron required for the stable nucleus. And this instability is also due to excess number of proton in the nucleus, and that means that the number of proton present in the unstable nucleus is more than required for the stable nucleus. So since the instability of the nucleus is caused either by the excess of number of neutron or the excess of number of proton, so accordingly beta decay is actually of two types. The first one is known as beta minus decay. Here I have written beta minus decay, and the second one is called beta plus decay. In fact, this beta minus decay is caused when there is an excess number of neutron over the number of neutron required for stability, and beta plus decay takes place when there is an excess number of protons over the number of proton required for the stability. We will actually discuss these two processes separately. First of all, we will see the concept of beta minus decay. In fact, when you say beta minus, that simply means electron. Electron is called beta minus. So, as I have told you just now, that if a nucleus is formed with more number of neutrons than needed for stability, then a neutron will convert itself into a proton and move towards stability. And actually in this process, an electron and an anti-neutrino are created and emitted from the nucleus. So in this process, in a simple way, you can say that a neutron will convert into a proton, and at the same time two other particles are created, and those two other particles are electron and antineutrino, and these two particles get emitted from the parent nucleus, and we get a daughter nucleus. So the process is like this. You can see this is the neutron n, which has been converted into proton, and at the same time the electron E minus and nu bar, this is antineutrino, have been created and emitted from the nucleus. As I have told you earlier in the first lecture, that this antineutrino is a fermion, just like electron and proton. This is also a fermion, and its mass is very small, or simply we say that its rest mass is 0. But as it is a fermion, so its spin is half. It is a half spin particle. Okay. This electron which has been emitted from the nucleus, this electron is actually known as beta particle or beta minus particle, you can also call it. So in fact this beta minus is simply electron. There is only a difference of origin. When this electron is emitted in this nuclear process, then we call it beta particle, but this is nothing, this is simply electron. Okay, so all properties of this beta minus will be same as that of an electron. Okay, now if you consider that there is a bulk of unstable nuclei, a large number of unstable nuclei, and all those unstable nuclei suffer beta decay, then there will be an emission of a large number of electrons or beta particles. And when a large number of beta particles are emitted from a bulk of unstable nuclei, then we call the simply those beta particles as beta ray. Now this beta decay process, as you have seen here, is just a conversion of neutron into proton, and the actual process we will consider a nucleus, and that nucleus will suffer the beta minus decay process or the electron emission process. So what will be the result after this beta emission? You can see from this process. Let us consider that our parent nucleus is X, whose atomic number is Z and mass number is A. It means in the parent nucleus there are Z protons, and the total number of nucleons is A. When beta minus decay or electron emission will take place, you know, one of the neutron will be converted into proton. So the total number of nucleon will remain unchanged, because there is a decrease in the number of neutron by 1, but at the same time there is an increase in number of proton. So as a whole, Z plus N will remain constant, that will remain A. Why? Because you can see Z has been increased by 1 and N has been decreased by 1. So the sum of these two remains same. That's why the daughter nucleus after this electron emission will have the same mass number as that of the parent nucleus. So you can see that this daughter nucleus Y has the same mass number A. But since one of the neutron has been decreased and one of the proton has been created, so there is an increase in the number of proton, and number of proton is called the atomic number. So the atomic number after this electron emission will increase by 1, and that's why the atomic number of this daughter nucleus is now Z plus 1. You can see it. Okay, and this is your electron emitted from the nucleus and antineutrino emitted from the nucleus. At the place of this E minus, you may write beta minus. So this process of beta decay may be represented by this equation 2, which I have mentioned it here. Actually, this decay process is known as beta minus decay process, and the emitted particle is called beta minus particle. Okay, so what is this beta minus decay and what type of daughter nucleus you get after this decay process? I hope you have understand. Now we will see what will be the Q value of this process. You know, Q value of the process is found by this equation, Q equal to Ui minus Uf. You know it. In fact, you know that Ui is what? Ui is actually the rest mass energy of the initial constituents, and Uf, this is rest mass energy of the final constituents. Now see this equation. Equation number 2, you can see in initial constituent we have only a parent nucleus, that is which is X. But in calculation of this Q value, I have assumed here the atomic mass of that nucleus, not the mass of nucleus. But in the first expression I have written Ui equal to mx times c square. What is this mx? Mx is actually the rest mass of the parent nucleus. Mark it. This capital Mx represents the rest mass of the parent nucleus. But if you want to express this mass of parent nucleus in terms of mass of the atom from which this nucleus belongs, you can write like this. You know, an atom is actually composed of two parts. First one is your nucleus and the another part is the circulating electrons. So nucleus plus electrons form an atom. So if you want to find the mass of the nucleus, you can simply subtract the total mass of the electron from the atomic mass. When we will subtract the mass of total electrons from the mass of atom, then we will simply get the mass of nucleus. So at the place of mass of nucleus mx, I have written here m of zxa minus zme. Actually here this m of zxa, this represents the mass of the atom x. It is not it is not the mass of nucleus, but it is the mass of the atom. And when we will subtract the total mass of electron from this, we will get the mass of nucleus. Now, as in this atom there are Z protons, so there will be also Z electrons, and mass of one electron is Me, so the mass of Z electron will be Zme. So after subtracting this Zme from the atomic mass, we get the mass of nucleus. And so Ui is simply equal to m of zxa minus zme times c square. This is the rest mass energy of the parent nucleus. That is the initial constituent. Okay. Now see again this equation. In the product, you can see there are two particles. One is electron and another is actually the neutrino, and there is a daughter nucleus. So in the final products, you can see there are three particles or three components: daughter nucleus Y, electron E minus, and antineutrino nu bar. So when we will actually multiply c square with the masses with the sum of masses of all these three components, then we will get actually the mass of the final constituents. But remember, antineutrino has no mass, its rest mass is 0. So in calculating the rest mass energy, there will be no contribution of this antineutrino. Okay, only the rest mass of the daughter nucleus and the electron will contribute into the rest mass energy of the final constituent, because antineutrino is massless. Okay, so you can write the rest mass energy of the final constituent like this. This is my plus me times c square. What is this my? My, I have assumed here, this is rest mass of the daughter nucleus Z plus 1 Ya. Mark it. This capital My represents the mass of the nucleus. But as in our calculation we are considering the mass of the atom, not of the nucleus, so again we will find the value of My in terms of the mass of the atom of the daughter nucleus. And if we consider that mass of the atom of the daughter nucleus is m of z plus 1 ya, then we have to subtract from this mass the mass of the total electrons present in that atom. Then you will get the mass of the nucleus, because mass of atom minus mass of electron will be equal to mass of nucleus. And since this daughter nucleus has Z plus 1 proton, you can see, so it will also have Z plus 1 electron. So the sum of the masses of Z plus 1 electron will be Z plus 1 into Me, where Me is mass of the 1 electron. So m of Z plus 1 Ya minus Z plus 1 Me, this is actually equal to My. Okay, so instead of My, I have written here m of Z plus 1 Ya minus Z plus 1 Me. And apart from it, there is an electron, so we add the mass of electron here, Me, and times c square. This is actually the value of UF. Okay. Now, to get the value of Q value of the process, you will use this equation 3. We will simply subtract this UF from UI, and you can see the expression. When you will subtract UF from UI, what will be your result? You can see this minus ZME in the expression of UI and minus ZME in the expression of UF will cancel out. And at the same time, you can see here there is minus Me and plus Me both. So that those two Me will be also cancel out. So simply you will get UI minus UF equal to mass of ZXA minus mass of Z plus 1 Ya. And that's why you can see I have written here that the Q value of the process is this much. This is m of ZXA minus m of Z plus 1 Ya times c square. This is the expression for the Q value of the process. Now, you know that 1 U or 1 AMU, this is equal to 931 mega electron volt. You have definitely an idea of it. 1 U is equivalent to what? 931 mega electron volt. So if in this equation 4, if all the masses present in this equation 4 are in the unit of U or AMU, then we will simply multiply this difference of mass by 931 to get the Q value. So instead of multiplying by c square, you can find the Q value of the process by this expression. This is m of ZXA minus m of Z plus 1 Ya times 931 mega electron volt. But remember, this formula can be used only when these two masses are given in the atomic mass unit. Okay, so this is the expression for the Q value of this process. Now, as you know, you have also seen in the previous lecture that this Q value which is evolved in this process, that energy is actually shared by the products as kinetic energy. And in the product you have seen there are three constituents. One is the daughter nucleus, another is electron, and the third one is antineutrino. And you know the daughter nucleus is very heavy, and as its mass is very large, so it actually shares a very little amount of kinetic energy. And we can neglect that amount of kinetic energy which is shared by the daughter nucleus. So we simply consider that the daughter nucleus does not share any kinetic energy. So total value of this Q is shared between only the two particles, the electron and the antineutrino. Okay. So I have mentioned it here. You can see Q is shared by the anti-neutrino and the beta particle. Now, what amount of energy will be shared by electron and shared by the beta particle? That is not fixed, but you will see that depending on the fraction taken away by the anti-neutrino, the kinetic energy of beta particle can be anything between 0 and a maximum value of Q. What does it mean? It means when the anti-neutrino shares the total Q value, then kinetic energy shared by electron will be 0. But when the total Q value is actually absorbed by the electron as kinetic energy, then the energy shared by the anti-neutrino will be 0. But in fact, in general case, a part of energy will be shared by the anti-neutrino and also by the electron. Actually, the variation of this energy of electron in against of the relative intensity, or you may call relative number of the electron, how this energy is shared, that has been shown in this graph. You can see the electron energy is varying continuously from 0. Here for this point, let us consider this point is P and this point is Q and this point is R. You can see that the energy of the electron varies from 0 to a maximum value at Q. At Q, kinetic energy of the electron is maximum, and that will be equal to the Q value of the process. Okay, and in between these 2 points P and Q, actually the energy will be shared both by the electron and the antineutrino. Corresponding to point P, the total energy is shared by the antineutrino, and corresponding to this point Q, the total energy is shared by the electron. Okay, so this was all about the beta minus decay. Now we will see the another process which is called beta plus decay process, in which you will see that a positron is emitted. Positron means an antiparticle of electron. As I have told you earlier that when there is an excess of proton in the unstable nucleus, there is an excess of proton than needed for stability, then actually this beta plus decay takes place. In fact, what happens in this process? If there is an excess of proton, the nucleus will have definitely a tendency to lose the number of proton, and at the same time it also tends to increase the number of neutron to get the stability. And for this, inside the nucleus there is a conversion of proton into a neutron. So if the unstable nucleus has excess of proton than needed for stability, then what will happen? Then actually a proton will convert itself into a neutron. But when a proton is converted into neutron, in this process, actually two other particles are also created and emitted from the nucleus. And what are those two particles? The first one is called positron E plus, and the another is neutrino, that is nu. In fact, this positron is simply the antiparticle of electron. There is only one difference between the positron and electron, that the electron has negative charge, but a positron has same positive charge, and all other properties of positron and electron are same. If you say that mass of a positron is what, that will be simply equal to mass of an electron. Okay, so this beta plus decay process takes place like this. You can see a proton is converted into a neutron, and at the same time two particles are created. This E plus is called positron and this nu is neutrino. Okay. Now, to see this process in actual manner, let us consider there is an unstable nucleus whose instability is due to the excess of proton, and that nucleus is ZXA. Okay. Now, this nucleus suffers beta plus decay, and you know, when you say that this nucleus will suffer beta plus decay, that is the positron decay, what does it mean? It means one of the proton of this nucleus will be converted into a neutron. So there will be a decrease in the number of proton by 1. So if the number of proton was Z in the parent nucleus, then there will be Z minus 1 proton in the daughter nucleus, because 1 proton has been decreased. On the other hand, 1 neutron is created, so the number of neutron will be increased by 1. So now the total number of nucleons you can see in the daughter nucleus will be what? That will be Z minus 1 plus N plus 1, and that will be simply equal to Z plus N, and that is equal to A. So the resulting daughter nucleus has an atomic number which is less than 1 from the atomic number of the parent nucleus, but mass number of this daughter nucleus is same as that of the parent nucleus. Okay. And at the same time you can see there is a positron and a neutrino emitted in this process. In fact, this E plus is denoted by the symbol beta plus. And so this process is called beta plus decay process. And this emitted particle, that is positron, in this condition is called beta plus particle. And again you can say that if there is a bulk of nuclei, then we will have a large number of beta plus particle emitted from that bulk of nuclei, and that will be called beta plus ray. Okay. And so this is the process of beta plus decay. Now again we will calculate the Q value of this process. The calculation of Q value of this process will be also exactly same as that was in the case of beta minus decay process. So you can say that the Q value of the process will be Ui minus Uf, and you know what is this Ui. You have studied this thing several times, so I am just repeating the same thing. In fact, Ui, you know, this is rest mass energy of the initial constituents, and Uf denotes the rest mass energy of the final constituents. Okay. Now see this equation, that is equation number 2, and find Ui and Uf. See, in equation number 2, the initial constituent is our parent nucleus X, whose charge number is Z and mass number is A. This is just nucleus, and we will find the rest mass energy of this nucleus. You know, if you want to find the mass of a nucleus, you can do a simple calculation. We will simply subtract the mass of the total electron present in the atom of that nucleus from the mass of the atom. Then we will get actually the mass of the nucleus. So M of ZXA here represents the mass of the atom X, and when the mass of total electron, that is Z times Me, will be subtracted from it, then it will be the mass of the parent nucleus. So Ui is simply equal to M of ZXA minus Zme times C square. Okay. And similarly we have to find Uf. Again you can see in the final constituent there are 3 components. One is the daughter nucleus, another is the positron, and the third one is the neutrino. Just like antineutrino, this neutrino has also zero rest mass. So in calculating the rest mass energy, the rest mass energy corresponding to neutrino will be equal to 0. So we will not consider this neutrino in calculating the value of UF. So you can think that the rest mass energy of final constituent will be simply the rest mass energy of the daughter nucleus plus rest mass energy of this positron. Okay? And what will be that? You can see this UF will be m of z minus 1 ya minus z minus 1 me. Actually, this m of z minus 1 ya is what? This is mass of the daughter atom, not nucleus. And z minus 1 into me, it is the total mass of z minus 1 electrons present in the daughter atom. So when we will subtract the mass of electron from the mass of atom, we will get simply the mass of daughter nucleus. So the first two terms actually represents the mass of the daughter nucleus. And there is one positron emitted, and mass of positron is same as that of mass of electron. So I have added here me and times c square. Okay. Now you have defined ui and uf. So from the definition of q value, now we can find what will be this q. You can see when you will subtract this uf from ui, you will get this expression. This q is equal to m of zxa minus m of z minus 1 ya minus 2me times c square. Okay. Here m of zxa, remember this is mass of the atom x, not mass of nucleus. And m of z minus 1 ya, this is mass of the daughter atom. And me is mass of electron or mass of positron. So this is the expression for the q value of this beta plus decay process. Again, you know, if all these masses, mass of the parent atom, mass of the daughter atom, and mass of the positron all are expressed in AMU or U, then we will simply write the expression for the q value like this: q equal to m of zxa minus m of z minus 1 ya minus 2me times 931 mega electron volt, because you know 1 mega because 1 u is just equivalent to 931 mega electron volt. It means when a mass of 1 u is converted into energy, we get 931 mega electron volt energy. Okay. Just like a beta minus decay process, you can also say here that since the daughter nucleus is very massive, so it does not share any appreciable amount of the energy from this q value. The complete q value is shared between the positron and the neutrino in the form of kinetic energy. So I have mentioned it here that q value is shared as kinetic energy of the positron and the energy of the neutrino. Okay. Now you have seen that two nuclear processes, that is there is a conversion of n into p, and at the same time you have seen that E minus and anti-neutrino is created, and again you have seen that a proton inside the nucleus is converted into a neutron and a positron plus a neutrino. But these processes, as you have studied, take place these processes take place inside the nucleus. But now a question arises. The conversion of proton into neutron, or this process, that is P equal to N plus E plus neutrino, is this process possible when the proton is isolated? It means if the proton is not inside the nucleus, can this process proceed? Yes or no? Answer will be no. If the proton is isolated, then it cannot be converted into a neutron. Why? What is the reason? In fact, you know, any nuclear process is energetically favorable. It takes place only when Q value of the process is positive. Only then that process will proceed. But in this process defined by this equation, as you know, the mass of proton is less than mass of neutron. In fact, proton and neutron are not equally massive. Proton has slightly less mass than the neutron. I have mentioned here the masses of these two particles in terms of energy units. You know, the mass of proton is almost equal to 938 mega electron volt per c square, and mass of neutron is 939 mega electron volt per c square. So you can see mass of proton is slightly less than mass of a neutron. And you know, if mass of proton is slightly less than mass of neutron, then see this equation for the Q value. This m of zxa will be smaller than the value of this m of z minus 1ya. So Q value will be what? That will be negative. Q value will be negative. And if Q value is negative, you know the process is not energetically favorable. And so we simply say that an isolated proton does not beta decay to neutron. It means if the proton is outside of the nucleus in isolated state, it cannot be converted into a proton. But at the same time, when a question is asked to you that an isolated neutron can be converted into a proton or not, answer will be yes. And reason is same. As you have seen that neutron is slightly massive than the proton, and so for this process, conversion of neutron into protons, see this process, the Q value will be positive. And if Q value is positive, it means this process is energetically favorable. So this process will proceed. It means a neutron in isolated state, even in isolated state, may be converted into a proton. But a proton in isolated state never be converted into a neutron. Okay, I think you have understand the fact. So in this lecture, we have seen actually the beta decay process, the two types of beta decay process. But in the forthcoming lecture, we will now see the rigorous theory of this beta decay process, and that rigorous theory is actually called Fermi theory of beta decay. And that Fermi theory is actually a vital theory, a concrete theory, a quantum mechanical theory to explain the beta decay process.